Okay, hello and welcome back to part 2 of the Machine Learning and Chemistry series. Once again, this seminar series will be delivered with an undergraduate target audience in mind. Today, however, we will be going through a short Jupyter Notebook tutorial for predicting partition coefficients, but the aim will not be to train a perfect machine learning model. Rather, here I'll try to sort of demonstrate some of the key tools and methods available to train a simple multi-layered perceptron forward propagation neural network. So for those of you who have been here for the previous seminar talks, by now hopefully you should be familiar with the use of Jupyter Notebooks, plotting libraries like matplotlib, gradient descent, and also hopefully some of the basic principles of machine learning. But if not, I would suggest that you at least familiarize yourself with some of the key principles and concepts of machine learning by going back to watch part 1 of this video series, where we did discuss some of the basics of linear regression and the causes of overfitting, etc. Hopefully that should catch you up to where we're at now, basically. Okay, so we're back to today's seminar. We're going to plot through each of these cells in the Jupyter Notebook together, trying and starting with a quick recap, hopefully, of linear regression. But before we can get started with that, we first need to install and import the necessary libraries and softwares. So for this tutorial, we will start by importing some of the generic libraries such as NumPy, Matplotlib, Pandas, CSV, etc. And then for our chemical descriptors, we're going to keep it simple today and use the RDKit chemoinformatics package. And then, of course, we will also need to choose a a machine learning package. So here we will stick with scikit-learn for now, as hopefully that will be the simplest and most straightforward package that you can use at the moment. So I think in the last seminar we discussed the relevance and the variety of applications of machine learning and chemistry, perhaps a very generic and very generalized, but what we perhaps ought to highlight is the primary reason for its popularity and usage in many computational labs, and that is cost. And so by cost, of course, we mean how computationally taxing or long a given calculation can take to run. So in the chemical sciences, we're often running quite expensive first principles electronic structure calculations to calculate a variety of chemical properties. Now, although they offer higher accuracy, they are typically very computationally intensive, which limits their use. So by contrast, machine learning can provide us with an inexpensive substitute for making these predictions. And so over the past 2 decades or so, you could say, past decade or 2 decades, we've seen a huge surge in the use of machine learning models in all areas of chemical industry, from materials modeling to drug design. So, it's everywhere now, right? So it's important that we sort of try to introduce some of the basic principles at least at the undergraduate level. Right, so we've mentioned that for this tutorial we'll be using scikit-learn as our machine learning package of choice, and for our descriptors we'll hopefully look at using 2D two-dimensional feature vectors using the RDKit chemoinformatics package. So do check out the links and search for the installation instructions yourself if you don't already have access to these on your computer. But these are the 2 links that you might want to look at. Okay, so for linear regression, or for supervised machine learning, linear regression is the model that finds the best fit between 2 given variables of interest. And so in the last seminar, I think we gave a very generic example of soil nutrient concentration versus crop yield. Of course, regression in general involves building a model that attempts to predict a continuous quantity, whereby we map function f from input x onto variable x onto a continuous output variable y. Okay, but you should hopefully already be sort of familiar with that, both from the last seminar, but probably from school as well. So now that we have, now just as we have sort of supervised learning models, i.e. a model where we tell the algorithm what the labels are, so we train it that way, there are also unsupervised learning models, which is where we do not inform the algorithm what the labels are. So it's important to remember this distinction, but for the purposes of this particular seminar, we are going to be focused on just the supervised machine learning, but more specifically regression tasks, okay? Not the classification. Right, okay, yes, okay, so again, as you'll probably remember from school, a simple regression takes the form of the following equation, where b0 is the intercept and b1 is the coefficient of the slope. And now to get a better regression estimate, we need to adjust the gradient b1. In essence, we need to reduce the loss function. And so this is done iteratively using the process of gradient descent. For a quick refresher on gradient descent, I will leave the link to the seminar video below because we have covered that in this series. So as we've discussed previously, the loss function or error estimates we can use to quantify the fit of our model. So the one we'll be using here is the mean absolute error. This is the average of absolute differences between the actual and the predicted value. It is the second most commonly used regression loss function. It essentially measures the average magnitude of errors in a set of predictions without considering the directions. So this is essentially a type of loss function. There are a couple of others you can use, but this is probably the most popular. So as I've said, to reduce the loss function, we use gradient descent. The gradient descent algorithm takes steps in the direction of the negative gradient. The gradient descent algorithm essentially, this is essentially to reduce the loss function as quickly as possible. But sort of more on that in the previous video on gradient descent. I won't go into that here. Okay, right. So the first step that we'll probably want to look at is importing data. So now we've all caught up. We can start by discussing the first step in building a successful machine learning model, which is selecting a suitable data set for training your model, which is generalizable enough to apply to the quantity that you're trying to predict. And that's quite important. So the first thing that you need is a large enough data set to work with. But there are a couple of things that you need to remember before you run off to train your model. I know it's very tempting to just take the data and start training it immediately, but there are several things that you need to take into consideration, and we might as well cover these things now. So the first thing you want to do is do some basic exploratory analysis on your data set. I can't stress that enough. It's really important. So make sure that the data set you're working with is consistent and that the chemical properties were generated using high accuracy methods. You could even look at the similarity between the data you intend to deploy on your model versus the training data using things like the Tanimoto or Fraggle similarity scores. These are things that you can find in the RDKit software package, so it's not difficult to use. And this step is really important because it will save you a lot of future headaches when attempting to deploy your trained model on new data, because that's the point, isn't it? It's not about testing it out and seeing how well it does. It's about feeding it brand new data and seeing how it performs on that. Right, and then of course it has to be generalizable. So to ensure that it is, you must take steps to avoid data leakage, meaning to prevent similar data, so in this case chemical structures, from appearing in both the test and the training sets, as this will give you false error estimates, most likely overestimating how good your model is, and then you'll find that it will spectacularly fail when deployed on new data. So it's important to avoid mixing at all costs. And for molecular prediction tasks, this can be best achieved using what's known as the Bemis-Merkel scaffolding technique. It's one of the methods where you can actually split the data, but in doing so, you're actually also making sure that you've got different, in this case, chemical structures in the different splits of data. Okay. So, and then finally, make sure that you have enough data, right? So the size of your data set depends entirely on the signal to noise ratio of your data. The more signal means you can get away with using a smaller data set. However, if you don't have a lot of data, it's important that you limit the complexity of your chosen model. So these are just a few things to consider. I'm sure this list could be even longer, but I think before starting training your machine learning model, these are the 3 things that I would recommend that you look into. Okay, so for this seminar, for this study, we will actually we will be looking at predicting octal water distribution coefficient. So for context, the n-octanol water partition coefficient, or the COW, is a partition coefficient for the two-phase system consisting of n-octanol and water. The partition coefficient essentially serves as a measure of the relationship between the lipophilicity, which is your fat solubility, and hydrophilicity, which is water solubility of a given substance. And so it's said that the value is greater than 1 if a substance is more soluble in fat-like solvents such as n-octanol, and then less than 1 if it is more soluble in water. That part is not really so important in our training of the machine learning model, but just remember that what we're trying to predict here is this partition coefficient. Okay, so step 1. Okay, so the step 1, let's load the data set. I found this data set on moleculesnet.org. There you'll actually find a whole list of interesting chemical databases to use for training a machine learning model. You'll have both experimental and some first principles calculations on there as well. And so we begin by reading it in. That's the first thing we do. So we've got this function here that helps you read it in. There are about 4,200 data points in this data set, and then for normalization purposes, later on I'm going to calculate the average experimental coefficient and the range as well. Okay, so hopefully in this table you can see that the molecular structures are represented in this SMILES string format. For those that aren't familiar with SMILES, they are essentially a line notation for describing chemical structures. It's actually just an acronym which stands for, remember, the Simplified Molecular Input Line Entry System, hence SMILES. Okay, so they're just these string representations of molecules. Okay, right. Okay, so then what we do is we normalize. We have functions for normalization, and then of course on normalization, when we predict, we calculate the normalization. We do this calculation here, and then the next step would be the descriptors, right? Okay, so great. Now we've got a data set which consists of SMILE structures and experimental values for the partition coefficient. Now we ought to find a way to represent our chemical structures such that a computer can understand and interpret them. And so that's effectively what the featurization process in machine learning is all about. Now we know that computers do very well with binary code, obviously. And so in this tutorial, I will try and show you how we can use 2D fingerprint representations of molecules to be used as your input X in your machine learning model. And so molecular fingerprints, like Morgan fingerprints, are fixed and a deterministic approach to get the vector to represent the molecule. So the learned vector mapping stays the same throughout the whole learning process. It's nothing like some of these more complex convolutional neural network stuff. It stays fixed and it doesn't change. So there is the option of 3D descriptors, which we won't go into here, but they will capture additional information, and many such representations remain invariant to translational, rotational, and permutational, which is really good. But today, we'll just focus on 2D descriptors. So here I've got a quick picture of different sort of requirements for molecular descriptors that you might want to consider. The most important, I would say, keep it simple. it should be possible to apply to local structure as well. So for your 3D descriptors, often they're applied to a global structure, but this would be helpful. I mean, these are all different examples and things that to keep in mind, but we won't go into that in this seminar. Okay. Right, so here actually I would like to quickly show you how we can visualize our molecular structures. So I talked about using the SMILES notation. So these are these molecular strings, so it might not be quite obvious what the molecules are, so it's nice to have a function that can help you visualize that. And we use RDKit to do this, so I do recommend that you go away and look at that and use that. So here we are, you've got the different representations of the molecules. You might notice that here you've got ammonia, which the SMILES notation is just an N. So that's just a little something for you to look at in your own time to see how you can actually visualize these molecules. Okay, so now before we sort of calculate the molecular fingerprints, we first have to actually convert the SMILES string format into an RDKit mol object. And we use that using this line of code here, mol from SMILES. You do that for all of your data points. So we had, what was it, 4,200 data points. Okay. So just to recap, I don't think I've explained in detail what Morgan fingerprints are. So just to recap, Morgan fingerprints are a fingerprint representation of a molecule where it looks at different substructures in the molecule. And if a given substructure is present in that molecule, it will index it as a 1 and in the vector array, and then 0 if it's not present. Okay, so it creates a bit vector representation, which is, of course, something computers are very attuned to dealing with, right? Okay, so great. Now we can calculate the fingerprint bit vector, but there are a few things that we need to specify first. So first thing is the size of your bit vector. Here I've chosen it to be 1024. Do you see the documentation for more details on how to choose your size? But then next you also want to sort of specify the radius, so how far out are you going to be considering the different functional groups. I've chosen a maximum of 5. Again, that's a parameter that you can probably optimize, but it's anything from 1 to 5 that you can choose. Okay. And then you can calculate your array of integers, right? And that's essentially what you feed in to your machine learning model. That's your X train. Okay, so you can see there's an array there. Okay, so now we have 2 variables that we'd like to map onto each other, and that's ready. We need to split our data set into a test and train sample so that we can later test the performance of our machine learning model. So to do this, there's a couple of ways of doing that actually. First, there's the straightforward, the random test train split. It's a 1-line code from scikit-learn, where you set aside 20% of your data set for testing and 80% for training. But then there are more advanced and more thought through methods like the k-fold cross-validation, where we sample over, say, 5 generations of splits, and with each iteration, the 20%, which is your testing sample, is represented by a different index. So this is actually quite a nice picture. You can quite clearly see what happens here. So in the first iteration, this is 20%, and then this is your training. In the second iteration, this is your 20% test, and these are the ones that are your training. And it does that for all 5 iterations, and once it's completed, it takes an average. So it's actually quite a nice, neat way of doing that. Okay. But there are other methods as well. This is perhaps the next step after the simple random split. Like I said earlier, there is the scaffolding technique, which is much, much, much better. Right. Okay, so that's your bit of code for doing the k-fold cross-validation there. Okay. Right, so now we want to train. Okay, so we want to train an ensemble of neural networks. So that meaning, in this case, we're doing 5. So where each neural network will be trained in the same way, and we will have the same structure as well, but it starts from a different initial set of connection weights. Okay, so weight optimization during training then becomes a set of your neural networks, and that all predict the target partition coefficient, but with each, has a different set of weights. Okay. I will, I'll reiterate here that I'm not sort of aiming to show you a perfectly trained machine learning model. In fact, I've not even optimized any of the following parameters. These were all randomly chosen. This is simply just to kind of demonstrate, what sort of code that you'll be looking at when training your model. But I will show you in a second that for optimize, what you can do to optimize your parameters and how to make it better. So, but for a network of 5 repeat ensembles, we are training a standard neural network with arbitrarily chosen parameters. We fit this with the X train, which is your molecular structures, and your Y train, which is your experimental partition coefficients. Okay. And then once you've trained it, this will take a couple of seconds, maybe a minute or so. Once you've trained it, you want to start testing it, don't you? So in terms of testing, you'll want to hopefully give it and feed it never before seen chemical structures, and so that's your X test. We loop over the number of ensembles so that we can actually calculate the average value for the coefficient. Of course, we want to evaluate the error metrics such that the MAE, like the MAE and the RMSE and the coefficient of determination. So that's essentially, those are your mean absolute error, your root mean squared error, and your R squared values. And we can actually print all of this here. So you can see they're not great, of course not. I mean, ideally you want to see something like 0.9 something, but it's understandable given the training that we have. Okay. So then, of course, a much nicer thing to do would probably be to actually visualize that. And so we actually plot this, where we plot the true versus the predicted value. So this is the machine learning, and this is the data that we had. This is your training data. Okay. So, again, it's not the best trained model, but you can see a general correlation between the experimental values and the machine learning calculated values. Right, okay, so before, when training the machine learning model, we said that we could probably do with a better trained model, and that there are a few ways of doing that. But since I'm sort of targeting this seminar for an undergraduate audience, I'm not going to look into the more complicated methods of optimization. Instead, we can just pick out one of the methods that you can get from scikit-learn, so that you've got this grid search CV function, which is really great because essentially what you're doing is you're creating a dictionary of options, right? So in the machine learning model above, when we were training it, you might notice that we've used the really function as the activation function, but there are, all these other ones that you can choose as well. So essentially you're feeding it a menu of options, and you do the same with the hidden layers, you do the same with the solver, and learning rate, etc. And then the idea is essentially to try and train it in such a way that it tries to select the best combination of options that will result in the lowest error. And then you can print these values out as well, and then go back and retrain your model on these better parameters. But one thing I will mention is that, for example, in this data set that we're using about 4,200 data points. That's an extremely large number. So instead, what you might want to do is take a portion of your data set. Of course, try to take a balanced portion of your data set, and then run the grid search CV, because you're essentially running this big calculation of this big matrix of values. So you do need to consider how computationally expensive it is to try and optimize these parameters. So do try and take a sample instead of the whole thing. Okay, right. Okay, so one of the last things you might want to do is you might want to look at the learning curve. So here, this is actually an example from a different machine learning model, not this one. But the idea really is just to kind of show you what I mean. A training curve here is essentially tells you how many training points do you really need to get the errors as low as you possibly can. So if you look at this particular example, you could probably say around 8K, right? The errors don't go any lower after that. And that's an interesting and a good way to kind of test your model to see how many training points are really sufficient. Maybe you've used too many, maybe you haven't used enough. So that's a nice test to kind of see how things are developing. Okay, so, and then the whole point of this is, of course, to be able to deploy new data. That's kind of the end goal. So once you're happy with the quality of your model, you can use it to predict new partition coefficients by feeding the model nothing more than just the chemical structure. Okay, so and then finally, sort of to cap things off, I think I want to quickly share a really, really good link to this paper that I've read. I've talked about a few of the points in there earlier when describing the do's and don'ts of the data sets that you should use and so on. So, so there's this there's a guide written for machine learning. This guide is actually written for machine learning practitioners, but I see no reason why an undergraduate audience shouldn't be able to follow it. If anything, it will essentially pre-warn you about the things to avoid, making it a good place to start. So highly recommended for me. Do click on this link. I will post this Jupyter notebook along with the video afterwards. Okay. So I think that's it. I hope you've gained some level of understanding, or at least an introduction to some of the key steps in training a super simple machine learning model. There's so much more I could have covered, but I hope this will sort of serve as a springboard for you to go away and learn any of these topics in more depth and detail. So thanks for tuning into the seminar, and I think that's it.